Hello my friends of Hatari Labs, my name is Saul Montoya. Welcome to this tutorial. This tutorial will be about the dynamic simulation of Hillslope Landslide with openFoam. So this tutorial will deal about how we can assess the dynamic simulation of debris. Okay, so this is a non-Newtonian. The debris is a non-Newtonian fluid, so actually where viscosity is dependent on velocity. Yeah, I want to show you, to start this tutorial, I want to show you a video, and this video is of debris flow. Let me show you this. Look, there is there has been already a landslide here, but there is another one, and check how water is fluid at high velocities, but here here where velocity decreases, actually it already became a solid again, or well, it became solid. Okay, so we want to assess this with openFoam, okay, because this kind of dynamic assessment is in order to have some probabilities of failure scenarios. If you want to do some contingency plans or emergency response, something like that, you have to assess how will it collapse and which will be the final geometry. Okay, so in order to do that, we have openFoam. We have a problem here, Non-Newtonian fluids. Okay, and okay, let me show you here. This is the model. The model is already run, but for you it takes 6 seconds, but I will somehow clear it because I want that you keep this I want to show you the procedure how to clear a model. In Ubuntu, if you are working in Linux, you can do command to do that, but in Windows you have to do it. You have to replace the alpha water and you here. Okay, here. Okay, so you have it here and nothing else. Okay, so this is actually what you will get. So this is the model. Okay, great. So let's talk about the model. First of all, we have, okay, let's go to the system. We have a control dict that we have a simulation of only 6 seconds, and where the output is every 0.1 second. Okay, what else? We have a block mesh dict that the output geometry of our model is pretty simple. It's just a box. Yeah, the box has 12 meters. Okay, let me show you the box because I have a figure of that. Okay, this is a box. This has 12 meters times 4 meters times 8 meters. So it's 8 meters high, 4 meters thick, and 12 meters long. Yep. Okay, so and this is the gradient. So actually we want more cells where the slope failure is, and we want less cells where there is no slope failure. Okay, we have two one model wall that is actually this face. We have the atmosphere wall and an outlet, because the failure will happen here and will start going this direction. Okay, so yep, and water will leave the model. What else do we have here? Let me show you what else do we have here. Yeah, so here we have talked about the control mains and the control dig. Okay, on the set fields we define that this part will be full of water. It's not water, it's actually mud or like earth, on liquefied air. Yeah, and then we have some as well, some set field for velocity, because actually this is the failure of the hill slope. Okay, so this is actually, this is not the stability of the hill slope. This is the failure of the hill slope, and the failure of the hill slope is where like precipitation has produced the saturation of the soil, or like there was an earthquake, something like that. So this has, I mean, the failure scenario is when there is an initial velocity, and the initial velocity that we assume on this simulation is that there is an initial velocity on the negative direction of the set coordinate of the z axis, that is of -1 meters per second on the direction of the z coordinate. Okay, this is this is how we have conceptualized the failure of the hill slope. Okay, yeah, because like in this okay, let me show you the transport properties. On the transport properties we have used the Birkarov coefficients, where at higher velocities there is less viscosity. Yeah, and if there is less viscosity, like the soil will become liquid and it will run or it will flow. Okay, yeah, and this is in this Birkarov coefficient. Actually, if you wait me a little bit, I have a figure for that. Let me Jupyter notebook, because I have done, I mean, I have played around with many because actually there are like 6 non-Newtonian fluid types in openFoam, and the Birkarov is one of that fits better with the flow dynamics. Okay, okay. Okay, I have done here okay, I have done here some charts where for this, yep, for this is the second, so we deal with the second. Let me show you. Okay, let me because I was playing around with this like a lot. Okay, and okay, this is this parameters. So this is the dynamic viscosity, the cinematic viscosity. Well, and this is the strain rate. So for higher velocities we have less viscosity, and when the velocity decreases, actually the fluid is more viscous. Okay, so it will require more energy for the deformation. Okay, great, so amazing. Okay, so we have this, and this is stated on the transport properties. Okay, and well, this is the geometry. actually these ones are some, if you want to play around, there are many parameters that I have done with custom, power law, Hershey-Buckley, and so on. But in this case, just Birka-Rowe was the one selected. But openFoam won't recognize these files because actually it's looking for this transport property file. Okay. And then transport property, we are dealing with turbulence on the K epsilon schema. And what else we have? On alpha water, we have the well, it's stated on set fields, but okay, these are the parameters for alpha water. Epsilon, this is related with the turbulence. Yeah, these are from the settings for the pressure, and these are the settings for the velocity. Yep, the initial settings, but please remember that set fields as well has some will replace these ones. Okay, but these are the boundary fields for the velocity, pressure, and so on. Okay, great. So far it's okay. What we are going to do is to start openFoam. Okay, but wait, I want that you, okay, once again, I don't know if I have done it, but okay, great. Okay, so we start openFoam for Windows. Then we do ls, then we go to, actually this is, it starts here, so we have to go to Non-Newtonian Fluids. No, disculpe. No, it's actually Non-Newtonian Fluids. ls Birka-Rowe. I don't know what's happening with me. Let me fix this. No. Oh, sorry, I don't know. Non-Newtonian Fluids, and this is Birka-Rowe. Okay, so Non-Newtonian Fluids, ls Birka-Rowe. Okay, ls, and then here we have just to follow some parts, that is some commands, that is block mesh, then set fields, then check mesh, and then interFoam, because actually we are going to deal with interFoam, and it will run for 6 seconds where the delta t is 0.06, so actually it will take some time. Okay, and okay, let me show you. Look, okay, we will stop this when the simulation is over, yeah, because I want to do, I don't want you to wait, like it will take 3 or 4 minutes, but I don't want you to wait for this, and see you in 3 or 4 minutes. Okay, see you, bye bye.